Good morning. In this class, we will study about applications of powder XRD method. There are three important applications. They are in determining lattice types, whether simple cubic lattice, FCC lattice, or body-centered cubic lattice. Two, lattice constants at unit cell length A for cubic unit cell A equal to B equal to C. Lattice constants, unit cell lengths are determined. Interplanar spacing can be determined, can be obtained from powder XRD. We know for cubic crystal system, the relation between interplanar spacing, unit cell length and HKL, Miller indices, is given by this relation. According to Bragg's law equation, n lambda equal to 2d sine theta, where theta is the glancing angle or angle of incidence of X-ray on the particular plane. For n equal to 1 for first order reflection, d equal to lambda by 2 sine theta. Let us substitute d equal to, in this equation, 1, 3 in 1. On rearranging, let us take out sine theta here, and on squaring and rearranging the equation, sine square theta equal to lambda square by 4a square h square plus k square plus l square. So k equal to lambda square by 4a square. Therefore, sine square theta equal to k into h square plus k square plus l square. From the powder XRD spectrum and using the above equations, we can determine the following: lattice types, lattice constant, and interplanar spacing. The powder XRD diffraction pattern or lines for primitive lattice is shown here. This is the powder XRD pattern for BCC lattice. This is the powder XRD lines obtained for FCC lattice. For HKL plane, 100 plane, h square plus k square plus l square, therefore 1 square plus 0 square plus 0 square 1k, that is sine square theta equal to k into 1, therefore 1k. For primitive lattice, all lines are observed, all lines are present except 7k, and 15k. Okay. For BCC lattice, h plus k plus l values even only are present. So for example, 1 plus 1, 2, 2 plus 0, therefore even, and this is even, 2k, 4k, 6k, 8k are present. The spacing in primitive lattice is 1k. The spacing in powder XRD pattern is 2k, 4k, 2k. The spacing is 2k. For FCC lattice, HKL values all odd or all even. For example, let us see here 3k, 111, all are odd. Here you see 4k, this is 110. 0 is even. Remember, 0 is even, odd, even. Here even, 0 is even, therefore it is allowed. Here even, odd, mixed, it is not allowed, it is not permitted. Okay. Let us now summarize the selection rule for the powder XRD diffraction pattern. For primitive lattice, all the lines corresponding to each line correspond to one plane. All planes are present, all lines except 7K and 15K. 7K and 15K cannot be obtained because h square plus k square plus l square cannot be 7. For BCC lattice, the selection rule for reflections, allowed reflections to obey the Bragg's law to give constructive interference plus k plus l Miller indices, HKL or Miller indices, even only plus k plus l even only. For FCC lattice, the selection rule for allowed reflections or HKL all odd or all even. We will see one example and to understand that. Let us solve a problem, that is to determine the type of cubic lattice from the observed XRD spectrum of the polycrystalline sample, powder sample. This is the powder XRD spectrum obtained for the polycrystalline sample. In powder XRD spectrum, the intensity of each line, reflected line, plus angle of incidence, 2 theta, plotted. Each peak corresponds to a particular plane. From theta, from the angle of incidence, using the formula sine square theta k h square plus k square plus l square, these planes can be identified, these planes can be labeled. How the planes are labeled or identified? By using the equation we have described. In this spectrum, you see 1, 1, 1. All are odd, HKL, all are odd. All are even, 2, 0, 0. All are even, 2, 2, 0. All are odd. Therefore, HKL values all odd or even. This selection rule is followed. Therefore, this sample is of FCC, face-centered cubic lattice structure. Let us study another problem shown from the below powder XRD spectrum of cesium chloride. We have already studied cesium chloride is body-centered cubic lattice structure. This is the powder XRD spectrum obtained for cesium chloride powder polycrystalline cesium chloride sample. There are several lines observed. I have shown here only the selected lines to understand for you. The planes are labeled from the angle of incidence theta. The planes are labeled from the angle of incidence using the equation we have described earlier. Please study the equations. And for BCC, this is here you see one even h plus k plus l even 1 plus 0 even. Similarly 2 plus 0 even and 2 plus 1 plus 1 even. Therefore, for BCC lattice, this selection rule is obeyed. Therefore, this cesium chloride crystal belongs to body-centered cubic lattice. Okay, this is obtained from the powder XRD. We have studied one application. Let us see now how the interplanar spacing is determined, how the lattice constant is calculated. By using the above equations, we have already described from the angle of incidence, for the X-rays, of wavelength, monochromatic X-rays of wavelength, lambda. So lambda is known, theta is known for HKL plane. The interplanar spacing for Example D100 plane can be obtained from the glancing angle and the wavelength of X-rays used. Similarly, we can obtain from the interplanar spacing for the HKL plane. For the HKL, we know HKL, the plane 100 or 110 plane. The interplanar spacing is known. The Miller indices are known. The lattice constant can be determined. Similarly, from K value, from powder XRD spectrum, from K value, K equal to lambda square by 4a square, the K value can be determined. Okay. In general, the selection rule for powder XRD diffraction lines present for different types of lattices are tabulated as shown here. As I said earlier, for primitive lattice, any HKL lines will be allowed. For body centered, H plus K plus L equal to even. For face centered, HKL all odd or all even or. Similarly for FCC diamond and cubic, hexagonal closed packing. These are the allowed refractions from the powder XRD spectrum. The unit cell type can be obtained. Thank you for watching.